There we go. You see it?
Excellent. Yes.
Okay, perfect. I'm sorry for that delay.
Thank you.
Okay. Today we're going to talk about how we're moving Visual-FX Studios to the cloud using KubeVirt and Kubernetes. First, a bit of introduction about who we are. CoreWeave is a public cloud. We're a public cloud startup, which is, I guess, pretty unusual. We're competing with AWS, Google, GCP, Azure. We focus primarily on very compute-intensive workloads and specifically everything that leverages GPUs. So our customers are people doing rendering, molecular dynamics, neural net training, and also real-time type workloads with neural net inference, video transcoding, game streaming, and virtual desktops. And virtual desktops and also game streaming is where we have started using KubeVirt to provide very integrated platform into our Kubernetes stack. And we're going to talk a lot more about that in a little bit. Our client size ranges from anywhere to 50 to 4,000 GPUs per client, or around 2,000 CPU cores. So we target kind of mid to large consumers of compute as our clients. Our primary offering and the only kind of offering we had up until we deployed KubeVirt was Kubernetes on bare metal. So we run large multi-tenant clusters directly on bare metal on Linux. And this allows us to do really fast spin up of customer workloads, since we don't have to instantiate VMs, we don't have to allocate cloud resources. A user can spin up a pod or 10,000 pods in 20 seconds. So it gives a really quick responsiveness for when people want to spin up their workloads. Obviously, operating multi-tenant clusters has a lot of corner cases to deal with. We heavily rely on pod security policies, on network policies, static CPU manager, and static CPU manager also has some interesting things with KubeVirt, like the previous speaker spoke about. But that's kind of what's our core business up until this year, when the need for more virtualized infrastructure, and especially virtual desktops, came from COVID. All of our VMs that we run have at least one GPU in them, so we kind of put GPUs everywhere. And we'll talk more about that in a second as well. So for this presentation, I'm going to talk to one of our large customer segments, which is Visual-FX Studios. So these are kind of 3D designers and artists and video editing artists that make all the cool explosions and stuff you see in all the movies and TV shows. The typical traditional VFX studio setup had a lot of on-premise hardware. There's a powerful workstations with NVIDIA Quadro GPUs, at least 3 4K monitors, a lot of storage. Each of these VFX projects are 20 to 100 terabytes. So usually the studios have around 300 to 500 terabytes of storage on site in expensive storage clusters. And traditionally, they do all the rendering as well on premise on usually at this time pretty old CPU nodes, or also render on the workstations at night. And being elastic for them is really hard. There are people who scale up to AWS, but that becomes really expensive with S3 costs and egress fees. And also the spin-up times of instantiating VMs and so on AWS aren't great. There's also a shift kind of in the rendering industry where GPUs are becoming more and more prevalent than just CPUs. So as a company, we initially started out by taking on the render side only, where we encapsulated render software in Docker images and containers and ran it on Kubernetes and scaled up and connected to their on-prem storage. So this all changed about a year ago, a little bit less than a year ago, I guess, when COVID started becoming a thing. All of a sudden, you have all these companies that have so much compute locally needing to work remote. And working remote is not super easy when you're talking about this much data and this much compute. So what a lot of people did is they did remote desktop software to their on-premise workstations. Works fine until some of the workstations break and no one's in the office, or you need to scale up, or your office internet connection goes out. Other people moved some of their workloads and some of the virtual desktops to AWS or GCP to be able to scale them. Moving your entire production pipeline to AWS is pretty cost prohibitive. And it also has a lot of performance bottlenecks with around how S3 works and S3 transfer speeds and so on. So the kind of common design is you run your virtual desktops on Amazon, and then you connect over NFS to your on-premise storage, and it's not performance optimal, to say the least. So we had some of our clients then come to us this summer and say, hey, can't we just move everything to you guys? But you need to have a virtual desktop infrastructure for us where we can access remotely systems that have powerful GPUs in them, powerful CPUs, and are directly connected to our storage. And that's when we kind of found KubeVirt, and in the end designed a solution that looks kind of like this. So everything runs in the same Kubernetes cluster. We have KubeVirt for the virtual desktops, which all have at least one powerful NVIDIA Quadro GPU in them, and we use Teradici or Parsec for the VDI software, which then uses the hardware encoding in the NVIDIA GPU to provide a really powerful VDI experience. The VDIs then mount in block mode storage for the root disk from our storage clusters, which are Ceph. We run 4 petabytes of storage in each of our data centers. And for the actual visual effects projects, we mount them in using Ceph-FS via Virtio-FS. This was a bit interesting because Virtio-FS was very new when we started doing this. But once we got everything working, the performance is really good. We run tens of thousands of IOPS over Virtio-FS. And this allows the artists to work directly against the shared file system, the Ceph-FS, that also the render pods connect to directly to actually render the jobs. So once an artist designs a scene in the virtual workstation, they submit it using a render scheduler called Deadline, which is the largest render scheduler, which then runs natively in Kubernetes containers on our bare metal Kubernetes nodes. And then we use some auto scaling with Prometheus metrics to scale up the render pods depending on what render software is supposed to be rendered in, and this scales up also running on the bare metal nodes to render the scene. Pulls the data from Ceph-FS, and the render start time is around 20 seconds. So it's really quick reaction time, and we can throw 1,000 GPUs at this render, which allows people to render a scene that would have taken 2 days locally in their office to get it done in 5 minutes. By leveraging VDIs and virtual machines, artists can pick what hardware type they need. If they need a lot more powerful GPUs and CPUs, they can easily flip that. Since the root storage is on block mode Ceph-FS, block mode Ceph, then they can just move the root disk over. Super simple, while maintaining the kind of performance intensive processes of the actual rendering is still running on bare metal without any virtualization overhead. And finally, all of this, since it's running KubeVirt and Kubernetes, is orchestrated via the Kubernetes API. So there's only one interface people have to integrate with, and only one set of tools to manage both the virtual desktops and render softwares running on bare metal, which is really awesome. So why did we choose KubeVirt? I've worked with OpenStack in the past, and when I got the request to build a VM infrastructure, my first thought was that, oh God, we got to deploy OpenStack. Not only do I think that OpenStack is extremely complex, it's also would be another kind of complex stack to run in parallel with already a pretty complex Kubernetes stack. We also sat down and looked at all the integrations we'd have to do and basically rebuild a lot of what we already built for Kubernetes and how it handles storage, and even worse, how to get these two to interact. If we run, the bare metal render jobs in Kubernetes, but ran the virtual machines, the virtual desktops in OpenStack, how would they communicate with each other, how would the orchestration work, and it would look to be a lot of development work. And so then we started researching alternative solutions and kind of came across KubeVirt. I'd seen KubeVirt earlier, but didn't really realize how mature KubeVirt had gotten. So we started development on this this summer, and basically had a proof of concept product done in 2 months. So say the development really started for a production product in October, and we have migrated the customer fully from their on-premise setup plus AWS to us in December. So by leveraging KubeVirt, we could just shave off so much development time, and also provide a much better user experience for the user. We get the seamless integration between bare metal and virtualized workloads. We talked about sharing storage with the persistent volume claims and Virtio-FS that just kind of works out of the box, and users just need to manage the storage in one place, which is the persistent volume claims. We can use the same tools, kubectl, and APIs to manage both VMs and manage the pods. And we can manage our internal KubeVirt infrastructure like we manage anything else we do for GitOps using Argo CD. Network policies using our Calico CNI just works, applies to the VMs, don't have to do anything special there. We do billing by looking at resource consumption through the Kubernetes, through Prometheus and Kubernetes metrics that also just worked out of the box. We use Metal LB and some of our proprietary tools to allocate IPs and public IPs to pods and services, and they also just work out of the box with KubeVirt. So KubeVirt made our life a lot easier. And we've been really happy with it, and all access for it has been really solid. The customers love it. We have, I think, 70 people as we speak running KubeVirt VDIs with anything between 1 and 4 GPUs in them, which is pretty neat. So we also had to build some stuff around KubeVirt to make it a bit easily digestible. So we use a tool from Bitnami called KubeApps to kind of give a visual way to deploy Helm chart. So we package up all of our different applications, like the render software, deadline in Helm charts, and give users a user interface through KubeApps to deploy these themselves. So we did the same thing for our KubeVirt VDIs. We built a Helm chart for it and built a custom UI component to deploy these. This gave the users a graphical interface to be able to deploy a VM, select what region they want on it, what OS image, what GPU, how much CPU, and so on. And then this, in the end, just generates the virtual machine manifest. It generates the service manifests and applies a bunch of different sort of mapping tables, which OS image and version should you run, what node type should this run on. It turned into kind of a Franken chart. It is way too complex for what Helm was really intended for. So what we developed after that was what we call the virtual server operator. It should really be virtual machine operator, but the conflicts with a KubeVirt virtual machine name, so we had to pick something else. Even though I think virtual server sounds pretty ugly, so this is just an abstraction over both the virtual machine CRD and the service CRD. And also data volume CRD, where users can, with one single YAML manifest, create a virtual machine that attaches their shell file systems, creates swap partitions if they need that. It creates users using cloud in it. It just makes the user experience a bit nicer for people who are not really used to virtual machines. We also had to do a bunch of modifications to KubeVirt and CDI. We were very early using Virtio-FS. I think the Virtio-FS was merged by Vladik about 2 weeks before we started using it. And I don't believe there's a lot of other people than us who have actually tried to use it at any scale. We found a bunch of interesting bugs that we tried to supply bug fixes for. and most of them have been merged. Once we got Virtio-FS working properly, we have had really good experience with it, even though it definitely had some quirks in the beginning. We also filed a PR for CDI to be able to do cross namespace volume cloning using the CSI clone API. And we want to do this, obviously, to spin up VMs really quickly. When our customers go and spin up a new virtual desktop, they want it to launch within 30 seconds, and waiting for data, route this to copy is not really feasible. CDI didn't have any cross namespace functionality built in, and the way we do it is we keep one namespace with our kind of base virtual desktop images with CentOS and Ubuntu and whatever. We want people to be able to clone these to their own namespace. So we filed a PR for that we're waiting to get merged. We also had to fork the NVIDIA device plugin, because the default NVIDIA device plugin has a static map of PCI IDs, which is a pain to maintain. And it also uses different resource labels than the regular NVIDIA device plugin for Kubernetes. And since we mix Kubernetes native or non-virtualized workloads together with KubeVirt, we want the resource labels for GPUs to be the same across both for kind of documentation, ease of use, and billing purposes. How has our experience been contributing to KubeVirt? It's been pretty easy getting into the code, to be honest. Whenever we find issues, it's very, very quick for us to dig in, figure out where we need to change stuff, and make the changes, compiling it. The build scripts are very easy to push your own Docker images and just update your KubeVirt operator manifests. We have had a bit more challenges with getting our pull requests merged. The build pipeline often fails, and kind of have to assume that it's nothing we did. It's sometimes hard getting feedback on the pull requests from the maintainers. Vladik has been really responsive, but we have had a bit more trouble on the CDI part, where I think that merging our cross namespace volume cloning feature will be helpful for a lot of people. But right now we're kind of forced to run our own forks of everything. That's it for the presentation. I'd like to open up for question. We're also hiring for all different positions. We're kind of growing rapidly. So if anyone wants to write Go or work with KubeVirt or Kubernetes virtualization full time, please hit me up. Okay, I'll look at both Slack and the chat for questions.
Yes, there is a question. There was a question a few minutes ago, so just in case, I'm reading that one in the chat here. Christian was asking, how was your experience developing GPU VMs/features? So I guess, well, about.
Okay, I'm not sure. I like developing in KubeVirt or outside of KubeVirt. So I mean, in general, it was good. I think that the fact that it was an NVIDIA device plugin is kind of what led us down this path. Otherwise, we probably wouldn't have tried to do it ourselves. But, getting the GPU support working was really a non-issue. There are some quirks depending on GPU types and so on. If you allocate a lot of memory to a VM, you need to increase the resource request above what kind of KubeVirt does automatically. So there are some quirks when you kind of get into running really beefy VMs. There's also a really fun thing with UEFI firmware in QEMO, where you basically we can't get more than one GPU running in a VM. So kind of have to run some stuff on UEFI where we need UEFI functionality, and some stuff on BIOS where we just need a lot of GPUs in a VM. But in general, pretty straightforward. Works really well out of the box. I mean, pretty not much to complain about. We also, as our company's built our own GPUs, I like to think that we know GPUs pretty well. But kind of adding that into KubeVirt has not been an issue. And yeah, Vladik, I know about the generic device plugins, and we might / will migrate to that in the future. The issue around PCI IDs is there as well. We just need an easy way to manage that. We have a lot of different GPU types, and we buy all the new GPUs that NVIDIA release. We're NVIDIA cloud service provider partner, so we just need to make it easy to map those, update those mappings, and also kind of mask that from the user, so they don't need to know PCI IDs and stuff for everything they request.
Yeah, following the chat in order, Soumya, I'm not sure if it's a question or a comment, but it was a mention about that she's would be interested in your fork of the GPU device plugin.
Yeah, I don't think it's pushed anywhere public, but I'll push it and put it in the Slack later on.
Great, thanks. David was also curious about the scale of the KubeVirt clusters in terms of.
So the KubeVirt clusters, they're not specific clusters. So we run, as I said in the beginning, we run really large multi-tenant clusters. So each cluster will have about 1,000 nodes, and then we change these nodes from being kind of hypervisor nodes, which really means that we reboot them and PCI pass through all the GPUs, or they're regular Kubernetes nodes, and we flip that back and forth based on demand. So if there's a lot of demand for virtual machines, we have a system based on a cluster autoscaler that basically reboots the nodes, and they boot up with a new flag, and then passes through all the GPUs. Right now, I think we have around 150 VMs total running with at least one GPU each, and that's spread out over. We have anywhere between 4 and 8 GPUs in each node. So you can do the math there, but nothing's
okay.
So around 50 physical nodes that are running KubeVirt right now.
I see. So when a node in your environment, a node is either going to be dedicated to KubeVirt virtual machines or kind of more generic.
Yeah, exactly. It's going to be either or, since we do 1 gig huge pages for performance. So it's just we looked into doing it dynamically and kind of slice and dice things back and forth, but it's not really worth it. We're just gonna, it's either gonna be KubeVirt mode when everything is in huge pages, all the memory is allocated to huge pages, and all the GPUs are attached to VFIO, the pass-through driver, or they're gonna be in vanilla bare metal Kubernetes mode, and we just reboot them back and forth.
So I guess to follow up on that a little bit, I'm curious, we're always interested in hearing people that are running KubeVirt at scale, and I want to know, did you encounter any sort of performance degradation with scheduling time or anything like that as you scale up more KubeVirt nodes? I guess, did you encounter any limits that you'd like to share?
No, not in terms of number of KubeVirt nodes. That's also one of the reasons that I like KubeVirt, is it piggybacks as much as you guys can on the Kubernetes native infrastructure. So I know what I get. So it scales as well as any other pod. There's obviously some traffic to your API servers and so on, but it's so light that and we schedule a bunch of VMs at the same time and have had zero sort of performance issues or anything like that. And the startup time basically just works.
So time from schedule to actually starting up the VMs. I remember you mentioned somewhere in the presentation that there's a lag. There's, I don't know, maybe it's like 7 minutes in AWS or something like that.
Yeah.
Are you able to achieve quicker performance boot up time?
Yeah, significantly. And it depends a bit on what you're booting and OS. But the pod and from kind of VMI start to the pod is running, it's 10, 15, 20 seconds. And then another 30 seconds on top of that until the OS is booted. So we can have a VDI up in 30 seconds, assuming that all the Virt launches are cached and so on.
That's awesome. Yeah, that's really solid.
It's really neat.
That's what we were shooting for. I'm really glad that this is working for you. That's really impressive to see this in action. Thank you.
Yeah. Thank you, guys. Okay, more questions.
Yeah, there is a question following. Actually, there is a comment before the question by Vladik. Back to the topic of device plugins. I think the comment was, Vladik had a session yesterday in the KubeVirt Summit about this topic, about generic device plugins. So that might be relevant to the previous comment. So that's
it will, and I commented on that a bit earlier that we will definitely look into migrating to that. What's important to us is that we can mask PCI IDs and so on from the user to provide a very simple user experience, and also for that to can tie into how we do billing. As I said, we have a lot of different NVIDIA GPUs, so we don't really want to have to have a bunch of PCI IDs flying around in a bunch of different configurations.
And in terms of questions, there's one here in the chat.
It's Longhorn, I think, is next one.
Exactly. Yeah. Are you using Longhorn?
So we're not. All of our storage is Ceph. Come back to architecture slide. So all of our storage is Ceph, which works really well for us. Ceph is great, but it's also pretty complex. There's a lot to manage. But at our scale, where we have 100 storage nodes across our data centers, I think Ceph is kind of the optimal solution. And we use the Kubernetes CSI there to orchestrate both read-write many volumes using Ceph-FS and the volume mode block volumes for the root drives. It works great, interacts very well with KubeVirt, interacts well with CDI and volume cloning. So we rely heavily on kind of volume cloning in CDI to clone root storage from new VMs, and doing that with zero copy and really quickly.
Okay, there are a couple more questions, but we are reaching the top of the hour, and I see that there is already a question in the thread in Slack. So
if you want me to answer there was a question about vGPU, which I think was pretty relevant. So we as a company, we stay away from vGPUs, both because for a bunch of reasons. We want to give the users full access to the GPU so they can do whatever they want with it. Also from a stability point of view, we just don't have a need for vGPU functionality, and our users traditionally want to have all the performance of the GPUs they get. We try to stock a lot of different GPUs, so we have everything from kind of RTX 4000s through V100s to A100s and A6000s, and we have to do PCI pass-through, which is an easier design, and our users like it. So that's why we kind of just have architecture to stay away from vGPU. And even if we did that, we would still have to deal with a huge page allocation for the memory, which is not super easy to allocate and deallocate 1 gig huge pages at runtime. So just dedicating nodes to be either KubeVirt or not is just a simpler architecture for us. And then the final question is, will it run Crisis? Yes, it will. I don't have any performance specs for you, but we also have a couple of KubeVirt test machines that we use in the office to test performance on different games. It's the 2 hours of QA we do every day. I'm available to Slack to answer any questions. Thank you, everyone, for listening to me.
Well, thank you very much for your session and for the presentation. That was great. And